Welcome to Tungal Online Classes. In previous video, we are discussed about the energy and the types of energy. Then, what do you mean by the energy? So, energy means the capacity of doing work. So, that is known as the energy. In energy, there are two types. One is the kinetic energy and one more is a potential energy, right? So, then what do you mean by the kinetic energy? So, kinetic energy means the energy possessed by the body by virtue of which its motion, so that is known as the kinetic energy. Next, the second one, potential energy. So, potential energy means the energy possessed by the body by virtue of which its position. So, that is the definition of potential energy. That is the definition of potential energy. Okay. So, here what is the definition of potential energy here? The energy possessed by the body by virtue of which its position. So, that is known as the potential energy. That is known as the potential energy. Okay, in potential energy there are two types. One is the elastic potential energy and one more is the gravitational potential energy. The first one is elastic potential energy and the second one is the gravitational potential energy. In that first one, elastic potential energy, it is very important for 5 marks. It is very important for 5 marks. So, then what do you mean by elastic potential energy? Okay. So, elastic potential energy means it is defined as the energy possessed by the body by virtue of which its configuration. So, that is the definition of elastic potential energy. Okay, what is the definition of elastic potential energy here? The energy possessed by the body by virtue of which its configuration. So, that is known as the elastic potential energy. Elastic potential energy. Okay, so then what do you mean by the configuration? So, configuration is nothing but length, size or shape of the body. Length or size or shape of the body. Okay, in this case, we are consider a spring. The one end of the spring is connected to the rigid support and the another end is free. Okay, see here, in this case, we are consider a spring. So, consider this is a rigid support, the one end of the spring is connected to the rigid support and another end is free So, already we know that when a spring is stretched or compressed, when the spring is stretched or compressed by a small distance, for example x distance, so in that case the restoring force developed inside the spring, it is trying to occupy its original configuration. It is trying to occupy its original configuration. Okay, see here, in this case we are not applying any force to this spring. So, the force at this end is 0. So, afterwards we are applying some amount of force to that spring. In that case, the length of this spring is increased. The length of the spring is increased. In that case, the restoring force is developed inside the spring. Okay, see here, the restoring force developed inside the spring, that is here, and the displacement of this spring in this direction. So, here the restoring force, it is trying to occupy its original configuration. This restoring force, it is trying to occupy its original configuration. So, here the restoring force is acting in this direction and the displacement of the spring, it is in downward direction. Okay, see here. So, from this one restoring force is directly proportional to displacement. Restoring force is directly proportional to displacement but in opposite direction. Okay, see here the restoring force is directly proportional to displacement but in opposite direction. To remove this proportionality constant, we use the extra term, that is K. That is K into minus X, right? This is equal to restoring force, that is equal to minus K into X. In this case, K indicates that is a spring constant. So, K means that is a spring constant. Here K is equal to, that is restoring force per unit displacement. So what is the definition of a spring constant here? That is restoring force per unit displacement. In this case, this minus sign indicates that the direction of the force, right? See here, in this case, the restoring force is acting in this direction and the displacement is acting in downward direction. Here, the restoring force is directly proportional to displacement and in opposite direction. Here minus sign indicates that the restoring force is opposite direction to the displacement. And to remove this proportionality constant, use the extra term, that is k. Then restoring force equal to minus k into x. Minus k into x, here k indicates that is a spring constant. Spring constant means that is a restoring force per unit displacement. Restoring force per unit displacement. So that is the definition of a spring constant. So in examination they may ask for 1 mark, define spring constant. The definition is restoring force per unit displacement. Okay, the next one, the external force. The external force acting on the spring, that is equal to restoring force but in opposite direction. Okay, see here, in this case this is a spring. So here we are exert some amount of force on the spring. In that case, the restoring force is developed in this direction and the displacement of the spring is in this direction. Here we are applying some amount of external force in this direction. So that is external force is in downward direction. Due to that one, the length of the spring is changed, right? In this case, the relation between the external force and the restoring force. The external force is acting in downward direction and the restoring force is acting in opposite direction. So then the external force, that is equal to minus of restoring force. External force, that is equal to minus of restoring force. So already we know the value of restoring force. Let us assume that this is equation number 1. Substitute equation number 1 in this equation. So substitute equation number 1 in above equation. Okay, see here. Then external force, that is equal to minus, as it is the restoring force value is, that is minus kx, then external force acting on the spring, that is equal to minus into minus, that is plus kx, right? So this is the external force acting on the spring. So this is our equation number 2. The next one, here we want to displace this spring by small distance, that is dx, right? So in this case we want to displace this spring, or we want to elongate the length of the spring through a small distance, that is dx. For that reason we have to do some amount of work done on the spring, that is small work done, that is equal to force into small displacement. Force into small displacement, that is dw is equal to F into dx. Okay, see here, again we want to elongate the spring from its mean position or its equilibrium position to some distance, that is x, right? Okay, see here, if the external force acting on this end is 0 means, so now it is in equilibrium position or mean position. So in this case we want to elongate the length of the spring from 0 to some distance, that is x, For that we have to do some amount of external work. So that is the total work done, that is equal to integration of small work done from 0 to x. Okay, see here we know that here dw indicates that force into small displacement. So here we know that to elongate the spring through a small distance, that is dx, we have to do this much amount of work done, that is dw is equal to F into dx. So next we are elongate that spring from equilibrium position to the maximum position or the extreme position, or 0 to x. For that one we are doing some amount of external work. That work is equal to integration of small work done. From 0 to x. Okay, see here. Then substitute dw value here. So already we know that the dw value here, substitute the dw value here, then w is equal to integration of 0 to x, then w is equal to, that is f into dx. Then what is the value of F here? F is nothing but external force. The external force value is, that is K into X. Substitute equation number 2 in above equation. Substitute equation number 2 in above equation. So then work done, that is equal to integration of 0 to x. The force value is, that is K into X with respect to dx. K into X with respect to dx. This is equal to, so this is equal to, in this case K is a constant term, take outside K, integration of 0 to x, integration of 0 to x, x into dx. So here K is a constant term, take it outside, then integration of 0 to x with respect to x into dx. So this in the form of x to the power is n with respect to dx, that is equal to x to the power is n plus 1 divided by n plus 1. So this is standard formula of integration. Just remember this formula, right? So here the n value is 1. Here the n value is 1. So then integration of x to the power 1 with respect to dx means, here n is equal to 1 means x to the power is 1 plus 1 divided by 1 plus 1. This is equal to x square divided by 2. So the value of this one is x square by 2. Okay, see here. Then work done, that is W is equal to, K into the integration of x with respect to dx value is, that is x square by 2. Bondings are 0 to x. Okay, see here. First substitute upper bonding value. So first one we take to this side. So then it becomes x square. Bondings are 0 to x. First we are substituting the upper bonding value. In place of x, substitute this value, x square, minus in place of this one, substitute this one, that is 0 square. So this is equal to k by 2 x square. So this work done, that is equal to kx square divided by 2. This work done stored in the form of elastic potential energy. That is 1 by 2 k into x square. Okay, see here. Then here k indicates that spring constant. So the definition of a spring constant is the restoring force per unit displacement. That is the definition of a spring constant. Okay, see here. The SI unit of this spring constant is, the SI unit is Newton per meter. CGS unit of K is, that is dyne per centimeter. And the dimension formula for K, right? Okay, see here the dimension formula I will write here. The dimension formula for force is m L t to the power is minus 2, and here displacement is L. So then dimension formula is, that is m L to the power is 0, t to the power is minus 2. Okay, see here the dimension formula of K is, that is m L to the power is 0, t to the power is minus 2. This is the dimension formula for spring constant. See here, in this case we are considered a spring, right? The one end of the spring is connected to the rigid support and the another end is free. Okay, already we know that when the spring is elongated or compressed through a small distance x, in that case the restoring force developed inside the spring, it is trying to reoccupy its original configuration. Okay, see here, in this case the restoring force is directly proportional to displacement in opposite direction, because the length of the spring is increased in this direction, but the direction of a restoring force is in this direction, because it is trying to occupy its original configuration. So that is, the restoring force is directly proportional to displacement in opposite direction. So next, to remove this proportionality constant, we use the extra term, that is K. Restoring force is equal to minus K into X, minus K into X. So then what do you mean by K here? K indicates that is a spring constant. So that is a spring constant. Spring constant means the restoring force per unit displacement. Next, so here the external force that is equal to restoring force but in opposite direction. For example, this is a spring, the external force is acting in this direction, the length of the spring is also changed in this direction, but the restoring force, it is acting in upward direction. So then the external force that is equal to minus of restoring force, that is equal to minus of restoring force. So next one, already we know that the restoring force value, so substitute here, then external force is equal to minus bracket of minus K into X, minus K into X. Here minus into minus is, that is plus, then external force is equal to K into X, external force is equal to, that is K into X. Okay, see here. After that, the small work done to elongate the spring through a small distance, that is dx, then dw is equal to force into small displacement. After that, we are going to elongate the spring from its mean position to extreme position, from 0 to x. So for that one, we are doing work that is equal to integration of small work done from 0 to x for mean position to extreme position. So then work done is equal to integration of 0 to x, f into dx here. Already we know that the f value, f is nothing but that is the external force, that is K into x. Substitute here, w is equal to integration of 0 to x, K into x dx. Here K is a constant term, take it outside. This is equal to K integration of 0 to x, x with respect to dx, x with respect to dx. So with the help of a standard integration formula, integration of x to the power n with respect to dx means x to the power of n plus 1 divided by n plus 1. So apply the formula to this one, right? The result of that one is w is equal to K x square by 2. The bondings are 0 to x, right? So take to this side, K by 2 is equal to, first substitute this value in this one, so that is x square. Next, lower bonding value in this one, so that is 0 square. K by 2 x square minus 0 square. So then w is equal to kx square divided by 2. W is equal to kx square divided by 2. So this energy stored in the form of elastic potential energy, it is denoted by U, that is equal to 1 by 2 K into x square. And this is about the spring constant. The restoring force per unit displacement, SI unit is Newton per meter, CGS unit is Ryan per centimeter, and the dimension formula is ml to the power 0, t to the power is minus 2, and the spring constant is a scalar quantity, Okay, see here, in this case, elastic potential energy, it depends on x value, If x value is more, the elastic potential energy value is also more. If x value is minimum or 0, then elastic potential energy value is also 0 or minimum. Elastic potential energy, that is U is equal to 1 by 2 K into x square. Here U is depends on x value because 1 by 2 is also constant term and this is spring constant. Then elastic potential energy is depends on displacement. Okay, see here we are going to draw a graph versus energy versus displacement, Okay, see here, in this case, if x value is 0 at mean position, for example, consider this is a spring, right? At mean position means the external force acting on the spring is 0. So then this is the length of the spring. So this is known as a mean position or equilibrium position. If x is equal to 0, the spring at a mean position, see here, at this position, the energy is also 0. If x is equal to 0, potential energy is also 0 at this point, right? If x is maximum, if you apply some amount of force to this spring, its length is increases, right? Or it starts oscillating in vertical direction. For example, this is spring, we are applying some amount of force to this spring means it starts oscillating, right? So in this direction. So here if x value is more, so that means extreme position, at extreme position the energy is more, and here is also the extreme position, the energy is more. At mean position or equilibrium position, the energy is 0. If we join this all the point, this graph indicates that the variation of elastic potential energy with respect to the distance, or with respect to the expansion or compression. Potential energy, there are two types. One is the elastic potential energy and one more is the gravitational potential energy. So elastic potential energy already discussed. The gravitational potential energy we will discuss in the 8th chapter. So that is in gravitational chapter. Okay. The next topic is law of conservation of mechanical energy. Law of conservation of mechanical energy. So this is also very important for 5 marks. It is also very important for 5 marks. Okay. See here, then what is the statement of this theorem? What is the statement of this theorem? Okay, see here, the total energy of an isolated system is constant. The total energy of an isolated system is constant, or the energy neither be created nor be destroyed, but it can be transferred from one form to another form. It can be transferred from one form to another form. So this is a statement of law of conservation of mechanical energy. So the first one, what is the statement of a law of conservation of mechanical energy? The total energy of an isolated system. The total energy of an isolated system is constant. The total energy of an isolated system is constant, or the energy neither be created nor be destroyed, but it can be transferred from one form to another form. So this is the statement of a law of conservation of mechanical energy. Okay, so next we are going to verify the law of conservation of mechanical energy in case of freely falling body. In case of freely falling body. Okay, see, in this case we are going to consider a body of mass m. Consider a body of mass m. It is placed at a height h from the surface of the ground. At a height h from the surface of the ground. So in this case we are going to verify the law of conservation of mechanical energy in case of freely falling body. So according to the statement, the total energy of an isolated system is constant. Okay, see here, the total energy means it is a sum of kinetic energy and potential energy, right? Total energy equal to kinetic energy plus potential energy. Okay, see here, so consider this is a point A, right? Consider this is a point A. Here at point A, we are going to find out what is the kinetic energy and what is the potential energy. Okay, see here, the kinetic energy at point A, that is 1 by 2 m into v square. In this case, the freely falling means the initial velocity or initial speed of the body is 0. If the initial speed is 0 means that is v is equal to 0. If v is 0, then kinetic energy at point A is 0. The kinetic energy at point A is 0. So next one, we are going to find out what is the potential energy. So potential energy expression is mgh. Here m is a mass, g is the acceleration due to gravity, and h is the height of the body from the surface. So here the height is, that is h, right? So the potential energy is mgh, right? Okay. The next one. So then the total energy at point A. So total energy, that is equal to kinetic energy plus potential energy. So here kinetic energy value is 0 plus potential energy value is mgh. Potential energy value is mgh. So then total energy at point A, that is mgh. The total energy at point A, that is mgh, right? Okay, see here. So at point A, the speed of the body is 0, the velocity, initial velocity of that body is 0. If initial velocity is 0, kinetic energy is 0. So then the potential energy at point A is, that is mgh. Then the total energy is kinetic energy plus potential energy. Kinetic energy value is 0. potential energy value is mgh, the total energy is mgh, total energy is mgh. Okay, so after some time that body covers through a small distance, that is x, right? So here we are assuming that this is a point B, right? So after some time that body covers a small distance, that is x. So here we are consider this is a point B. Then the total height of this body from surface of a ground to point A is h. So now the distance from this point to this point is, the total is h and it covers x distance. So then its value is becomes h minus x, h minus x. Okay, see here. Next, at point B, okay, at point B, the first one we are going to find the kinetic energy at point B. Kinetic energy, that is equal to 1 by 2 m into v square, right? See here, the initial speed or the initial velocity of an body is 0, but this body is moving from this position to this position. In that case, it acquires some velocity. We are going to find out what is the velocity of the body at point A with the help of an equation of motion, that is v square minus u square, that is equal to 2as, that is equal to 2as. So here the initial velocity of that body is 0. So then v square minus 0, that is equal to 2. A is nothing but in vertical direction, the acceleration is the acceleration due to gravity, so that is g. Next, s is nothing but a distance, so that is x, the distance is x. Okay, see here, this is the v value here, so that is v square is equal to 2gx. This is the velocity value. Okay, substitute here. Then kinetic energy, that is equal to 1 by 2 mass into v square value v is, that is 2gx. Here 2 get cancelled. Then the kinetic energy, that is equal to mgx. The kinetic energy at point B is, that is mgx. So next we are going to find out potential energy at point B. Potential energy at point B. Potential energy expression is mass into acceleration due to gravity into height. Here the height is this much, that is h minus x, because the total height from this point to this point is h, and this body covers small distance, that is x, up to this one. So then the height from this point to this point is, that is h minus x, that is h minus x. Okay, substitute here, that is h minus x. The potential energy is mgh, here h value is, that is h minus x. Then the potential energy of the body at point B is mg bracket of h minus x. So next one, the total energy, that is equal to kinetic energy plus potential energy. Here kinetic energy, that is equal to, that is mgx. Kinetic energy is mgx plus potential energy, that is mg bracket of h minus x, mg bracket of h minus x. Okay, this is equal to, right, this is equal to total energy, that is equal to mgx plus mgh, multiply this one, mgh minus mgx. In this case, plus mgx minus mgx get cancelled, then the total energy, that is equal to mgh. The total energy at point B, that is equal to mgh. Okay, see here at point A, the first one at point A, kinetic energy is 0 because initially that body is moving with a 0 speed or 0 velocity. Initial velocity is 0. Then kinetic energy is 0, then potential energy of the body at point A, that is mgh. Potential energy of the body at point A is mgh. So then the total energy of the body at point A, is kinetic energy plus potential energy, that is 0 plus mgh. Then the total energy at point A is, that is mgh. The total energy is mgh. The next one, at point B. At point B, that body covers some distance x with some velocity, that is v. So then the kinetic energy of the body at point B is kinetic energy equal to 1 by 2 m into v square. Here we are going to find out what is the velocity. So with the help of a equation of motion, we are going to find out the velocity, that is v square minus u square is equal to 2as. Here the initial speed is 0 or initial velocity is 0, v square minus 0 is equal to 2gx. Here acceleration of the body. So in this case, that body is moving in a vertical direction, we are consider that is the acceleration due to gravity. Okay, then velocity square, that is equal to 2gx. Substitute v value in this case. Here kinetic energy equal to 1 by 2 mass, v square value is 2gx, 2 get cancelled, then the kinetic energy is equal to mgx, kinetic energy equal to mgx. So after that, potential energy of the body at point B, that is potential energy equal to mg bracket of h minus x, right. So next, the total energy means kinetic energy plus potential energy. Kinetic energy value is mgx plus potential energy value is mg bracket of h minus x, mg bracket of h minus x. Here multiply this one, total energy is equal to mgx plus mgh minus of mgx. So here plus mgx minus mgx get cancelled. The total energy at point B, that is also mgh, that is also mgh. So according to the statement, in an isolated system, the total energy is conserved or the total energy is constant. At point A is also the total energy is same, mgh. At point B is also the total energy is same, that is mgh. So next we are going to find out what is the total energy of the body at this position. So in this case, that body is on a horizontal surface. So then we are going to find out what is the total energy of the body at point C. The next one, at point C. At point C. Okay. At point C, first we are going to find out what is the kinetic energy and what is the potential energy. First we are going to find out the potential energy. So potential energy at point C is, here that body is on the surface of the ground or the surface of the earth. In this case, height value is 0, h is 0. So then mg, h value is 0, then potential energy is 0. Then the potential energy is 0. So next one, we are going to find out kinetic energy. Kinetic energy is equal to 1 by 2 m into v square. Again we are going to find out the velocity with the help of a equation of a motion. So with the help of equation, that is v square minus u square is equal to 2as. So here v square as it is, initial speed of the body is 0, that is equal to 2 into g. So in this case, that body covers a distance. So from this point to this point means that is h, right. That body covers h distance. So initially that body is this position. Now the body reaches this position means the total distance covered is, that is h. Here s is equal to h. So then v square is equal to, that is 2gh. V square is equal to 2gh. Okay. Substitute v square value in this equation, then kinetic energy is equal to 1 by 2 m, v square value is, that is 2gh. Here 2 get cancelled, then kinetic energy is equal to mgh. Kinetic energy is equal to mgh. Then the total energy that is equal to kinetic energy plus potential energy. Kinetic energy plus potential energy. So kinetic energy value is mgh, potential energy value is 0. So this is equal to mgh. This is equal to mgh. Okay, see, at point C is also the total energy is same. At point C is also the total energy is same. So this is the proof of the law of conservation of mechanical energy in case of freely falling body. The first one we are consider this a point A, point B, point C, At point A we are calculate kinetic energy and the potential energy. The total energy is mgh. Next one, at point B, so after some time that body reaches to the position B, it covers a small distance, that is x. Then we are going to find out the kinetic energy, potential energy at point B. Here this is at point B, kinetic energy is mgx and potential energy is mg bracket of h minus x. The total energy is mgh. The total energy is mgh. The last one, at point C, the potential energy is 0 and the kinetic energy is mgh, then the total energy is mgh. So in this case, the energy at any point is the same. The energy is any point is same, but it is converting from one form of energy to the another form of energy. So at point A, the kinetic energy is converting into potential energy. At point C, the potential energy is converting into kinetic energy, right? So according to the law of conservation of mechanical energy, the energy neither be created nor be destroyed, but it can be transferred from one form to another form. Here it is transferred from kinetic energy to potential energy, or potential energy to the kinetic energy. This is the proof of this theorem. So now we will draw a graph versus energy versus distance. Okay, see here. So this is the energy and this versus distance, right? So initially at point A, the body is at A point, and in this case the potential energy is maximum. So here the potential energy is maximum when the body is moving towards the surface of the earth. In that case, the height of the body goes on decreasing. If the height is decreasing, potential energy is also decreasing, because the potential energy is depends on the height, right? If the height is more, the potential energy is more. In this case, at A position, the height is more. So after that, this body is moving towards the surface of the earth. Here, the potential energy goes on decreasing because the height of this body goes on decreasing. So here at point A, the potential energy is maximum. If the height decreases, the potential energy is also decreases. The potential energy is also decreases. Okay. The next one, kinetic energy. At point A, the kinetic energy is 0. The kinetic energy is 0. If the body is moving in the downward direction, the speed is increases. If the speed increases, kinetic energy of that body is increases, right? So at A position, the kinetic energy is 0. If the body starts moving downward direction, its speed goes on increasing. If the speed is increases, means the kinetic energy of that body is also increases. This indicates that kinetic energy of the body, and this indicates that potential energy of the body. But at any point, the sum of kinetic energy and potential energy is constant. Here is also same and here is also same. The next one, we are going to verify law of conservation of mechanical energy in case of simple pendulum. Okay, see here, consider this is a rigid support. So this is a rigid support. We are taken a string of length is L. The one end of the string or one end of a thread is connected to the rigid support. The another end is connected to a small body or the bob. Its mass is M. So that is bob, B-O-B, bob, right? Okay. So this is known as the simple pendulum setup. So in this case, we are consider a string or a thread. One end of a thread is connected to the rigid support. The another end of a thread is connected to the bob of mass is M. So let us assume that. So this is the string. The one end of the string is connected to the rigid support, and this is the bob. It is attached to the end of another end of the string, right? So here we are giving very small oscillation to this body. It starts oscillating in this direction, right? So here initially we are not apply any force on this body. In that case, that body is in equilibrium position or mean position. So now this body is in mean position because we are not exerting any force on this body. So that body is in mean position or equilibrium position. So afterwards we are applying a small, or we are giving a small oscillation to this body. we are giving a small oscillation means it's start oscillating between two extreme position. So here this is a mean position. So after giving small oscillation means it's moving in this direction and it reaches the extreme position. So this is known as the extreme position. Extreme position. So here we are giving small oscillation means it starts oscillating between two extreme position. Okay, so here in this case consider this is a horizontal surface. This is the horizontal surface. Here this is the position is A and this position is B and this position is C. So in this case first we are assuming that the body or the bob it is moving from point B to point C. So point B to point C, in this case the height of the bob from the surface of the ground is increases, right. So here when the bob is moving from point B to point C, here the height of the bob from the ground is increases. If the height is increases, the potential energy is increases. The potential energy is increases at extreme position. At extreme position, the speed of the bob is 0. At extreme position, the speed of the bob is 0. If the speed of the bob is 0 means kinetic energy at extreme position is 0 or minimum, right. Okay, see here at extreme position when the bob is moving from point B to point C, the height is goes on increasing. If the height is increasing, the potential energy is also increases. At extreme position, the speed of the bob is 0, so then kinetic energy is 0. So in this case, the entire kinetic energy of the bob is converting into potential energy. At this position, entire kinetic energy that is converting into potential energy, right. Okay. Similarly, when the bob is moving from extreme position towards the mean position or from point C to point B, in that case the height of this bob is decreases. The height of the bob with respect to the ground, it is decreases. If the height is decreases, the potential energy is decreases. Potential energy is decreases, but when the bob is moving from this point to this point, the speed of the bob is increases. The speed of the bob is increases means kinetic energy increases. Kinetic energy increases. At point B or at mean position, the height of the bob from the surface is 0. So at this position, potential energy is 0. Potential energy is 0. So here the entire potential energy is converting into kinetic energy. So here potential energy that is converting into kinetic energy at point B. But the total energy at any point is the same. At this point is also total energy is same. At this point is also total energy is same. So this is the law of verification of mechanical energy in case of simple pendulum. Okay, see here, just remember the points here. At mean position, the kinetic energy is maximum. That mean position, kinetic energy is maximum and the potential energy is minimum or 0 at point B. So this is the mean position. At this position, kinetic energy, okay, see here, mean position, kinetic energy is maximum, potential energy is minimum or 0. Next one, at extreme position, potential energy is maximum and kinetic energy is 0 or minimum. Okay, see here, we will draw graph versus energy versus displacement. Okay, see here, this is the energy and this is the displacement. So that is x value, right. Okay, see here, at mean position, kinetic energy is maximum. At mean position means this one. So this is a mean position. At this position, kinetic energy is maximum. Okay, then at extreme position, the kinetic energy is minimum. So that is 0. So these are the extreme position. Let us assume that this is a minus x and this is a plus x. Okay, at extreme position, kinetic energy is 0. So join this line. Okay, so this is about the kinetic energy. Okay, similarly, potential energy. Okay, see here, potential energy, it is maximum at extreme position and minimum at mean position, right? Potential energy is 0 or minimum at mean position. Okay, see here, at this position the potential energy is 0, right? Okay, so then the potential energy is maximum at extreme position. So here the potential energy is maximum at extreme position. So these two are the extreme position here. Join this one. So this graph gives the variation of energy with respect to the distance. Okay, see here, this curve indicates that kinetic energy and this curve indicates that potential energy. This curve indicates that potential energy. Okay, see here, this curve indicates that potential energy, but here the total energy at any point, the total energy at any point is same. At this point is also same. If you want to calculate the total energy at this point, the total energy at this point is also same. So total energy, that is equal to kinetic energy plus potential energy, right? So this is about the law of verification of a mechanical energy in case of a simple pendulum. So just remember the points here. At extreme position, potential energy is maximum, kinetic energy is minimum. In this case, entire kinetic energy is converting into potential energy. At mean position, the potential energy is 0, kinetic energy is maximum. In this case, entire potential energy is converting into kinetic energy. Thank you.